Yeah. So I hope now I should be able to share the screen. So it says host. Yeah. PowerPoint.
You are co-host now, so you can share.
Yes. Yeah. Yeah. So I hope you all. Uh, Again, once again, a good evening, and myself, Vinayak. Uh, I did my MSc back then in 2009, and as I remember, when Professor was saying the thing that there shouldn't be a discrimination between teachers and the students, I remember I was most of the time talking to many of my teachers, and that's the possibly one of the reasons that I still have a connect with them. I do share some good things. They appreciate, which also kind of feels good to you if they have some good happenings in their lives which they share with us. So, and both of us are kind of updated about each other. So likewise, I'm in touch with many of my teachers. I'm thankful to them, and I could see many of them in the viewers now. So I'm just happy as well as a little bit of you can say cautious as in whatever I'm going to speak. So okay, so the title of the talk says that the devil lies in the defect, and that most of us might have heard this phrase, the devil lies in the detail. I'll come to those details and the defects later, just as quickly as possible. um, all this introduction has been made, so I'm just going to skip. What I'm going to show is this: these young men and women, which form the group, research group of mine. So four of them are PhD students. Some of them have just passed out as MSc major project student. Couple of them have joined in, and couple of them are short-term summer interns, winter interns, and so on and so forth. So likewise, they bring the vibrancy to the lab. They do all the things, and I enjoy being with them in the lab. And most of the results that I'm going to show, the recent ones, except for my PhD ones, are being done by the instruments which are being made by these people, and which I'm going to anyways come to this thing. And the results are, of course, theirs. I'm just a catalyst. So some of the areas wherein we are working, as ma'am mentioned, I work on different aspects of materials. I particularly had my PhD in material science, so I work on different aspects of electronic transport properties, which could be revealed into either electronic transport, thermoelectrics, optical things like that. So and then it does have some kind of an applications to the real life. So if it can get into an improvement in the property, how does it, and so on and so forth. In the process, one learns a lot about what happens at the in the solids, in the physics, and so on and so forth. So our lab, basically we named it as smart lab because I could actually find a common thread among all the projects that we conduct. We can basically call them as smart materials. The smart materials are the responsive materials which responds to various physical stimuli, and the response is also kind of a physical quantity which could also be generalized into some kind of a categories. So I have kind of tabulated the response, the stimulus and the response, and there could be some kind of exchange between these, like some kind of optoelectronics, electro-optics, mechanics, thermoelectrics, and so on like that. So various of these things, the red one highlighted particularly forms our current projects. So we are dealing with photoconductors, photochromics, photothermals, thermoelectrics, we are dealing with chem resistors, and so on and so forth. So essentially, as you would see at the end of this talk, the essential electronic transport phenomena of these materials or solid, whatever we are seeing, basically is the underlying physics which we are trying to seek some kind of a insight. So let me just get to the point. Okay, so I gave it as a name that devil lies in the defect. The defect, what is that? First of all, we have to have an order, and then we have to have a defect. So first of all, let us start with crystals. So when I say crystal, possibly you get think of you can think of these things, something which is kind of expensive semi-precious stones, crystal. But when I say crystal, something which comes to my mind is this: it's basically a regular periodic arrangement of atoms, which is basically sitting on a mathematical construct which is called as a lattice. So a crystal, the way we define, it's basically periodic arrangement of atoms and ions, which is composed of a mathematical lattice, which is basically formed by different symmetry operations, translational, rotational, combination of these things, and so on and so forth. And onto those lies this basically the atoms, or which are called bases, and they form a crystal. So just to simple an example, one can imagine a crate where we put these eggs. So it has definite patches, pockets where the egg can be put. So even if the egg doesn't lie there, the pocket remains there. So that is an ordered sitting arrangement for an egg. Similarly, we have a mathematical construct of a lattice where the atoms and ions can sit. And these are essentially constructed by various symmetry transformations and so on and so forth. So one can see like that we can have a, so if there is a periodicity, if it repeats itself, one can find a repetitive unit which can basically repeats itself at particular distances in the space and fills all this 3D space. So one can imagine a periodic crystal, basically something which fills in with this periodic unit cells up to infinity in all the 3 dimensions. So one can then find out all the kind of symmetry operations that one has. We can apply and find out various possible ways in these can be arranged and so on and so forth. But why? First of all, the question is, why do they crystallize? So if at all, if something is forming a periodic arrangement, one should ask a question: why do they actually form such an arrangement? So of course, like every other reason in physics, the reason is to minimize the energy. So the crystal, when it forms, it helps in minimizing energy of the system. So basically, what energy are we talking about? If imagine there are two atoms which are brought in closer, there are if they are far apart, there is no force among them. As they are brought in closer and closer, the attractive forces increases. At some point of time, when the like charges starts repelling each other and things like that, the repulsive forces take over. So there is somewhere a optimal balance is struck at some particular distance, wherein they kind of like to do not want to leave each other or go further beyond. So that is an optimal distance, the bond length, that is when they come. And when many such atoms are brought in together, they will form some kind of a regular periodic position. They will keep social distancing of such a particular distance with among each other. So that forms a regular periodic arrangement into into a solid. And when such long range periodic arrangement happens, a long range electronic correlations also take place. So these long range electronic correlations basically results from the each individual electronic wave functions within the atom starts to interact with the neighbors, and basically the long range ordering happens. So you can imagine, when I have a single atom, I have discrete energy levels. I bring in 2, I bring in 3, and then the statistical weight goes on increasing for particular energy level, and then they form something which is called as a band. So the band basically would can say it is composed of several closely spaced energy levels, wherein the electrons or the charge carriers can actually take place. So essentially, then it would result into some kind of a lattice, which is resulting into some particular electronic bands, which basically can have within themselves some allowed or unallowed, I mean the forbidden energy levels. And these forbidden energy levels then can be called as a energy gap between the two bands, as we say. So like for example, here in this diagram, you can see at the interatomic distance a, there lies this particular position where there is a allowed band, which is two allowed bands which are separated by a certain distance. We call it as an electronic band gap. Now where do these these you can see on the right hand side there, I have shown several types of electronic bands. Some of them are degenerate with a heavy hole or lighter hole, which essentially deals with the the effective mass of these carriers in that particular lattice. And also, depending on the directions in the crystals, there can be momentum transfer involved within the I mean the excitation de-excitation or not. It that basically gives rise to either a direct kind of band gap. That means electron can directly, without any momentum transfer, can go into the higher energy level which lies in the conduction band, or it has to be accompanied by a phonon assisted transition where basically the some kind of a lattice vibration also comes into the picture. So all of these, I'm just going, I've started these things, but I'm just going pretty rapidly because I assume many of these MSc students would, if not now, but they might look at it later. So it would just help them into getting into what where I'm leading to. So essentially, all this electronic band structure arises because of this periodic lattice. And the periodic lattices, where you assume some kind of a periodic potential, you write down the wave functions, you write down, then you find that the wave function can somewhat mimic to that of free electron wave function, and so on and so forth. So all these things effectively lead you to a more complex picture of electron energies allowed and not allowed between those things. So something which we call it basically the band structure of a solid. So you can see in there are several the lines basically represent the electronic bands, and those are basically arising because of the particular lattice structure of this thing. So any changes in the crystal lattice are going to be reflected into the electron energy band structure, and so on and so forth. So the regular periodic lattice that we were talking about, the ideal regular periodic lattice, for example, if I take germanium, whatever crystal it forms, it would result into this particular density of states, and correspondingly the electronic band structure would look like this. So so that you will have a particular, so the zero energy which shows the Fermi energy up to which you will have some kind electron filled at 0 Kelvin. So at higher temperature it might lie somewhere in between to that of this thing. For metals it would lie within one of the bands. So then you will basically classify that as either a metal or an insulator or a semiconductor and things like that. So given all this, let's come back to the topic. What devil are we talking about? What are these defects? So we have seen what a crystal is. Basically, the next thing is basically crystal imperfections. So no such thing like a perfect crystal exists in the nature. Okay, so because basically we are imagining a perfect or ordered periodic lattice of atoms where everything occupies its own position at every possible lattice points, and that is what something which doesn't happen. What you would, if you look at the real crystals, you would see something like this. There are vacancies, there are defects, as in atoms are present where they should not be, atoms are missing from where they should be, there are lines of atoms which is particularly missing, there is an extra plane of atoms which has come in, there is a stacking fault in 3 dimensions. So all these things, these are imperfections of real crystal which could be classified based on their dimensionality. So when I say if the defect is associated with one particular lattice point, I would call it as a 0 dimensional defect or point defect. For example, you can see there are some vacant sites here which are called vacancies. There are impurities, a foreign atom which is sitting at a regular position, or there can be interstitials, or the atom which is present in a non-lattice site, and so on and so forth. Other than that, there are one-dimensional defects which are edge, screw dislocations, and like that. There are two-dimensional defects. Particularly, you can take an example of a surface. That itself is the biggest defect in a crystal. Then we have stacking faults. There are planes which are particularly missing, or they are additional planes coming into. There are three-dimensional defects like a void or a particular inclusion, which can actually change into the lattice periodicity. So all of these are possible. And what we are particularly in this context of this talk, we are interested is in the point defects. The point defects are the defects which are associated with one particular lattice point in a crystal. So why would a vacancy form, first of all? So even if everything is at its own place, isn't that nice? I mean, why would a vacancy would arise? I mean, why would something be absent? So essentially, you can imagine something like a class where all the students are sitting in their seats, but if a student has to go out, he has to make some kind of an effort. So essentially, it takes some kind of an energy to actually form a vacancy. So this vacancy formation is associated with some kind of a energy absorption into the lattice. So it is an endothermic process. However, when it forms, then what drives this? Basically, there is another thermodynamic quantity which is called as entropy. Most of you, I mean, of course, I mean, I refer to the student. Many of the students would be aware of it. The second law, we define the entropy, relates entropy with the lattice, I mean, structure, and so on, the configurational entropy, etc. So it quantifies the disorder in the system. Now you can imagine when you have created a defect, you have nucleated disorder into the system. So the entropy goes on increasing. So the amount of, so all both these quantity, that there is a trade-off between the entropy, the enthalpy and entropy, between the two things. The enthalpy, basically, we know that is the amount of energy required for this defect to form, and it is supposedly positive quantity, and it goes on increasing with the more and more defect as you go on creating. However, the entropy, on the other hand, basically that is also a positive quantity, but now they are going to balance each other, right? So as the temperature increases, the disorder in the system goes on increasing, and that somewhat stabilizes this thing. And you can see the largest entropy change that takes place is from a very ordered system to the first few disorder, and then when enough number of defects have been nucleated, the disorder somewhat kind of saturates. So somewhere in between, the addition of these two balances, and it might goes into the entropy changes actually surpass this energy requirements of enthalpy, and you would get a free energy which is negative, and that nucleate those that decides a particular concentration of defects in a crystal. So the thermodynamic stability of these things basically will govern how many defects will nucleate, what will be their configurational arrangements, and so on and so forth. And so there is a trade-off between these two thermodynamic quantities. And essentially the temperature of the solid, I said, as you go on increasing the temperature, the disorder in the system will kind of increase. You will have more number of defects created, because the thermal energy, as we have mentioned here, the thermal energy is basically one which displaces the atom from its equilibrium position. So more at higher and higher temperature, more and more thermal energy is available, so that which is reflected in the kBt. So this equation basically sums up that if n sites is the total number of sites where the defect can occur, which is essentially the total number of sites in a lattice, then it goes on exponentially with d by kt. So the CD is the defect concentration for a given temperature, and so on and like so forth. So in a given crystal, depends what are the thermal treatments, what is the processing condition, what are the how it has been grown, that particularly decides what kind of defects nucleate, what will be their densities, and so on and so forth. So all of these will lead to different interesting properties that we are going to see. So particularly, I would like to mention here the surface. We have said that anything which is missing from its position is a defect, and you can imagine the translational symmetry of the crystal is basically breaking at the surface. So beyond that, the crystal doesn't exist. So that is again a biggest defect in this system. So surface and interfaces are again one of the biggest defects in the system. And naturally, when you are going into smaller and smaller dimensions of the I mean materials, you are essentially increasing the surface, you are increasing the defects, you are increasing the devils that can actually participate into various things. So how do these devils reflect themselves, or how do they manifest themselves? Some of the examples which I have, these are my results, and these I would be touching upon. They would manifest themselves in terms of electronic transport. They would manifest themselves into some kind of a thermal transport, the heat transport, and so on. The optical absorptions, because of defects, we'll have a lot of energy levels present. we'll have spectroscopic changes in the system because the local chemical environments are changing, and so on and so forth. So all these things are these signatures can be basically investigated if one has to look into the effect of those things, particularly in the context of metal oxide semiconductors. When I say metal oxide semiconductors, these are binary or ternary metal oxides. You can imagine there's a metal ion and there is an oxygen in the lattice. These are ionic crystals. You can imagine like sodium chloride, which we regular our table salt. You will have sodium and chlorine, which are present in a regular FCC interpenetrating FCC type of structure. Similarly, if you have a oxide lattice, you will have a metal and oxygen, which are basically their occupancy will be governed by the symmetry, so where they can take place. So essentially, most of the times, it so happens that these anions form some kind of a environment about the metal ion. So, and then that particularly joins edgewise, cornerwise, and so on to make chains or planes or things like that, and that extends to 3 dimensions. So now in this case, what can happen? Either the metal can be missing or the oxygen can be missing. So in both these cases would lead to different electronic scenarios. Okay, so first of all, we can take an example where the oxygen is possibly missing. So there is a vacant, you can imagine there is, if the oxygen from an oxygen site leaves, you have a vacancy at an oxygen site. Effectively, to compensate, the crystal cannot be charge deficient or charge excess. So it basically has overall it's a charge neutral. So the excess charges basically are incorporated into the lattice to accommodate this vacancy. So effectively, when an oxygen is missing from the lattice, several electrons, I mean for a oxygen which is divalent, so it will have 2 electrons donated to the lattice. And similarly, if there is a metal ion which is missing from its place, you can basically imagine there is a vacancy at a metal ion place, and that leads to excess positive charges into the system. Which so in either case, we are kind of we are incorporating either a donor impurity, which gives rise to a n-type conduction, or a acceptor impurity, which gives rise to a p-type conduction. So the excess electron would make this thing as n-type, and the excess holes or excess positive charges are going to make it into a p-type material. So these things you can see from the diagram here. So okay, just a minute. So this thing is basically, it shows that the concentration of defects on y-axis compared to the oxygen partial pressure of synthesis. So at higher and higher oxygen partial pressure, you would expect that it is oxygen rich. So and lower oxygen partial pressure, it will be deficient in oxygen. So the vacancy concentration is much higher at low oxygen partial pressure, the oxygen vacancy concentration. On the other hand, if it is rich in oxygen atmosphere, you will see that the metal vacancy concentration is much higher. It is oxygen rich, and somewhere in between, it basically has a balance between the two. So that is stoichiometric thing, which hardly happens in the real crystals. So many of these oxides are either metal vacancy rich, or the oxygen vacancy rich. So or I like that. So correspondingly, they will have either a majority hole type conduction or a majority electron type conduction. So I'm just okay. Yeah. So you can see that there is a AX shown here, which is nothing but your A is your, let's say, metal, and X is your anion, which is an oxide. If one of them is higher than the other, so then it basically reduces to either n-type, or the opposite increases, it reduces to p-type. So the excess metals will have metal vacancy, excess oxygen will have metal vacancies, which will give some acceptor level near the valence band maxima, and that would ionize at room temperature and will donate some kind of hole to the this thing, and we'll have excess hole carriers. On the other hand, if you have excess oxygen vacancies, which can lie just below the conduction band, and they can also, I mean, at room temperature, most of these are ionized, and they will contribute to electrons to the conduction band, and you will have excess electrons in the system. So either ways, If it is otherwise, there are native donors like oxygen vacancies, it is very difficult to dope it with p-type, because inherently or by thermodynamically it likes to go into oxygen vacancy state, because that has the minimum free energy of formation, and correspondingly you will have very high energy of formation for a metal vacancy, and correspondingly you will have no acceptor impurities, and if there is no acceptor impurity, you will not have any p-type conduction. And subsequently vice versa, you can say about the acceptor, if it is native acceptor type, it is very difficult to dope it with n-type. So in either ways, it is strongly having some kind of a dominant carrier concentration. One of the majority carrier concentration exists. Now, let's say we have an n-type uh, n-type material, and we have these donor states which are just below this conduction band. And at room temperature, let's say these are ionized, so we are showing that they are open boxes, and there are some negative charges which it has contributed to the conduction band. And there exists some, so this solid, this semiconductor would be anyway having some kind of a surface somewhere, and that surface will be interacting with the atmosphere, and atmosphere will kind of lead to some kind of surface states, that these are nothing but some kind of chemisorptions which are happening on the surface. And these chemisorption related, what does these surface states do, as in they are close to the EF, so you will have some electrons going into these surface states. Correspondingly, the potential here will show upward rise. You will have some depletion layer created on the surface because of these surface states. So similarly, one can imagine that for a p-type semiconductor, you will have the downward bending bands, which essentially denotes that you will have hole accumulations on the surface. It is a negative opposite depletion in case of holes. So all these defects which are lying on the surface, or they are so the first which are interior are giving you some kind of donor or acceptor levels. The which are on the surface are going to give you some kind of band bending or depletion layers, and that will result into changes in the electronic or optical transport. So I would start with my result. This is particularly the first most result I started with working in my PhD. And you can, as the name suggests, it says defect-induced magnetism. So in otherwise, you will have ferromagnetic samples where you will have magnetic ions, like some transition metal ions or something, which will have some kind of unpaired spins, and those spins will have different moments, and those that will give a overall moment. And these spins will start talking to each other. There will be a long range order, and they will start having an exchange interactions, which will either give you a paramagnetic or ferromagnetic or ferrimagnetic type of interactions. But the context that I'm talking about here is actually magnetism in non-magnetic materials. So if there is basically a material like that which does not have a permanent magnetic moment, and if you find that it shows up something like that, it is surprising. And that is the same thing which happened to me when I was working. I was working with this tin oxide material, which is otherwise a diamagnet, for some other purpose, and I wanted to learn one of the magnetic characterization system. And the person who was operating, he asked me, do you have a magnetic sample? I said, I don't have. He said, anyway, you can bring in some dummy sample. So I took this and I went there. We did it on that vibrating sample magnetometer. And to my surprise, I got a somewhat noisy ferromagnetic loop. And I was surprised that either I have got some kind of impurity, or this machine has gone bad. These were the only two possibilities I could conclude at that time. And what I found was that it was indeed showing. Then we made some more magnetic measurements on more precise system, which is squid magnetometer, which can detect very low magnetic moments in the sample. And that confirmed that it indeed had some kind of a magnetic moment, and it was showing a saturating magnetic moment with the field. So then we started doing tracing what could be the reason, I started reading the literature. So I would present the story this way. So this material was actually made by a method which is called as solution combustion synthesis. So the name itself says it's a combustion synthesis. It's a really exothermic process. You can see the fire here. It burns off with fire during the synthesis. So for momentarily, very high temperatures are reached during the synthesis. It is around 1500 degrees C or something like that. So, and suddenly that flame goes off when the fuel runs out after a few flash of seconds. It just cools down to room temperature, or let's say very low temperatures, near room temperature. So whatever defects what can form at higher temperature for that flash of time, it basically forms, and it gets quenched to room temperature. And then if this hypothesis was correct, then if we heat treat the sample to higher and higher temperature, we should actually anneal all these defects, because the thermal energy is going to bring in some kind of order into the system, and that will anneal these defects, and you will get much better crystal. You will get rid of the grain boundaries, which wherein most of the defects can occur. You will get rid of the vacancies, because the structure will try to refine itself. So then I annealed these samples at different temperatures. As you can see in the XRD and the Raman particularly, the Raman of the as prepared sample, which was basically quenched from high temperature, it showed a very large defect related Raman mode, which was not supposedly to be present in a regular crystal of SnO2. This is not allowed by the symmetry and Raman active modes of SnO2. And then on the other hand, when in the annealed sample, as you can see, it just goes on reducing and reducing in the intensity as we went on annealing at 400, 600, 800 degrees. The 800 was near somewhat like a bulk crystal, bulk sample. And the 1500 degree, which I did later on, was actually very sharp peaks with absolutely no defect modes and so on like that. So you can see in the XPS spectrum also, we saw some kind of peak which would so XPS results from the core level photo emission from the sample. So you shine the material with X-rays, and you get a photoelectron emitted from the material. And this photoelectron, since it is coming from characteristic energy core levels, you can basically measure the binding energy or the kinetic energy of that emitting photoelectron, and normalize it. I mean, subtract it from the incident photon energy, you will get the binding energy of that electron, and that is a fingerprint of a particular element composition. So when I say oxygen 1s, the S basically says that it will not have any spin orbit coupling, and I shouldn't expect any splitting in the peak. But I was getting a high peak at higher binding energy, which essentially reflects that there are some fraction of oxygen which are not present, or which are nearing to a non regular crystallite location. So this was further confirmed. So then we did more magnetic measurements on these on the annealed sample. As you can see, the annealed sample, the saturation magnetization went on decreasing, and even the hysteresis kind of disappeared. And then we did some temperature dependent measurements and simulated those things with a combination of ferromagnetism and paramagnetism. Basically, you can see that at low temperature, it shows more of a 1 by T type of variation, which is like Curie behavior. So it's somewhat paramagnetic at low temperature, and at ferromagnet, it still has this flat something which can possibly point at some ferromagnetic interaction. Then we did this electron paramagnetic resonance onto these samples, and people have done DFTs. They have calculated what should be the G value if there happens a unpaired spin in the vacancy site. So these vacancies can actually work like a trap states. They can trap single electron, they can trap two electrons. So when it traps single electrons, it is paramagnetic. It has some kind of a I'm sorry, this is going by itself. It has some electron spin associated with it, and if they are so large in the density, then they can talk to each other. There can be a long range or exchange. Then there are, I mean, it was quite recent then, I mean, about just in the beginning of 2000 decade, people had just started looking at defect induced ferromagnetism, and people then started putting forward the theories that if a non-magnetic semiconductor I have, um, if a non-magnetic semiconductor I have, it will have, I'm sorry, this is just going by itself. It wants me to speed up. Okay. So there wouldn't be any spins, and it would show some kind of a diamagnetic behavior. If there are spins which are present at regular periodic sites, like a regular ferromagnetic system, you will have spins which are in particular order. They will have some exchange correlation J, which will give rise to ferromagnetic ordering. However, if there is something like this where there are vacancies and they are trapping these electrons which can have unpaired spin, which can basically give rise to some kind of a moment into the sample, people proposed some bound magnetic polaron a magnetic polaron. That means this electron spin associated with some lattice vibration, or polarons, basically some kind of a effective charge due to lattice distortions, and those couple each other at if they are such a large in density, and then they can give rise to long range ferromagnetic order. However, if they are not in the such large densities, they can actually remain isolated. So the reports on these systems were all over the place. Some people were saying it is paramagnetic, some people were saying it is ferromagnetic, some people were saying it is not at all ferromagnetic, and so on and so forth. There were even reports where people said it could be because of the stainless steel tweezer people are handling. So I try to avoid all those things. And essentially what it boils down to is that it boils down to your processing condition, how you are making it. That basically tunes the defects, and correspondingly the density of these defects, which essentially triggers whether it is going to have some kind of a moment, if at all moment exists, whether it will be having a long range order or not, and so forth. So I we did some more work based on that, and we in fact I'm just tried to synthesize this by various other ways, and try to dope it with some magnetic ions to increase the to see what happens to these moments. And chromium, which is also not really magnetic, actually it is like iron, cobalt, nickel, it doesn't have a moment, it's unpaired spin. So the chromium dope enhanced some kind of a ordering when we looked into the nature of chromium dope samples, the dilute magnetic semiconducting things. So it so happened that when you dope it with chromium, you you actually putting this chromium at tin site. Chromium is essentially trivalent and tin is for tetravalent. You are creating somewhat charge imbalance. Just to accommodate that charge imbalance, there would be one oxygen vacancy associated with this chromium doping, each of this doping. And that, how would you confirm that? If you are looking at the lattice vibration of these octahedras of 6 oxygens with this tin, SnO6 octahedra, and similarly you will look at the octahedra of chromium O6, you will see that if you are replacing this different charge ion with this 4 plus, you are creating one vacancy in one of these 6 oxygen sites, and effectively this symmetric stretching which is happening will not be there. So that particular mode of Raman excitation is killed systematically. And as you go on doping more and more of this different uh, nuclear charge, you will see that this mode gets killed systematically, and other modes starts to show up, which are basically ascribed to the foreign atom, the new one. So that's how we actually looked into that, and the electron paramagnetic resonance further confirmed that the signal due to the oxygen vacancy which we had actually ascribed to, it went on increasing with more and more chromium doping. So that further strengthened the claim that it happens. But then there was a catch, that if you go on doping something in the crystal, there's a limit to which it can digest. After that, it will start throwing it up into interstitial sites, or it will start phase segregating out. So that is called a solubility limit. So it so happens that for chromium into tin oxide, the solubility limit is reached by 2%. Beyond that, if you dope chromium, it will go into interstitial sites, and those interstitial site chromium will go back to its native antiferromagnetic exchange. So then you will start having two competing phenomena of ferromagnetism due to these vacancies and antiferromagnetic exchange because of these interstitially present other ions, chromium 3 plus. So there were different signals identified in EPR spectrum, and you can see that some of them systematically increased. The fourth one is actually oxygen, this one, and it sorry, 5-1 is actually oxygen vacancies, and this is a large reference signal. First one, the long one is basically the ferromagnetic long range resonance, and the third one is when the chromium dopes into the tetravalent site. And then Curie-Weiss plot further confirmed that it is ferromagnetic up to 2%, which says CR2, and then it showed some kind of when it went into 3% doping, it showed a negative intercept on a Curie-Weiss plot, which means there was an antiferromagnetic ordering taking place. So this was explained, as I said, the vacancies now can actually couple through some of the substituted chromium sites. So that is called as, it's some kind of a super exchange which is taking place among these different magnetic ions, and that is through this thing. I'm sorry, ma'am, how much time do I have? Like, could you please tell me? Now it's almost 5:30. So I'll just, hello? Hello? I can't hear you.
You can take.
Hello.
Hello. Yeah.
Yeah. Okay. So maybe I can take some time. Yeah. So okay. So the next example that I'm going to show, two examples. One is the defect. How do they play a role in the gas and solid response? First of all, we have seen there will be some kind of surface state formation, and those surface states are participating into the transport properties. Secondly, I would take it into further extend into thermoelectric transport and things like that. So the first one, just to get acquainted with this idea of gas sensor materials, these are nothing but semiconductors whose conductivity is basically changing with the ambient atmosphere gases. So some of the gases like oxygen are basically electron trap states. I mean, they are electron acceptors. So when oxygen gets absorbed, it basically reduces the carrier concentration, and so on. If there are gases like hydrogen, it donates an electron and it will change the carrier concentration in opposite side. So this diagram here, it shows large variety of materials which have been used for this purpose. So essentially one can say that if you have a semiconductor which has sufficiently large band gap with a possibility of having a surface state where the depletion width will sufficiently tune the electrical conductivity, your job is done. But then people looked into better and better material candidates because they wanted superior application related performances, and just getting a change was not enough. People wanted large change, people wanted selective change, people wanted the change to happen at a particular temperature like room temperatures and so on like that. And that is where all this understanding of gas sensor mechanism and things like that brought in. So I have mostly worked into oxides and 2D materials like graphene and MOS2 and things like that. I am going to show a couple of results on zinc oxide. These are the one which are which basically acts like some kind of a barrier between the two grain. Changes with the gas atmosphere, you have essentially made a responsive material which responds to the gas. So ZNO was like the first material to be discovered. You can find these sensors in various places domestic to all these strategic applications. But The basic fundamental thing is that you have a semiconducting wherein you have a surface state adsorption, which is either electron donating or electron accepting material. Now, then it becomes kind of looking at the response of the ZNO, but these ZNO needles, as you can see in the scanning electron microscopic image here, these are single crystal like needles, and they are fairly large in size. They are of the order of few microns. So it is essentially something which has very long range, very large crystal, and the grain boundary effect I was talking about, those are hardly 2 to 5 nanometers. So that is insignificantly small compared to the within the grain transport or within the crystal transport. So what we saw was that instead of so when we expose it to gas like hydrogen donates some electron, the depletion kind of reduces, and you will see that the current increases, and it saturates. And it saturates when you remove the gas, it comes back. It varies with the different gas concentration. But for some of the temperatures, what was happening is that it was increasing and it decreased suddenly back. And it then the equilibrium was reached after much longer time. You can see the time scales are of the order of 10,000s of seconds. Absolutely, this is a very bad sensor, I would say, if that is the case. If because you want a quick saturation and you want a quick recovery, which is happening only at 300 degrees. But anything lesser than that, it was showing this kind of a overshoot. Okay, so then we were looking into what could be the reason for this, and started reading lots of papers wherein people said hydrogen being a smaller gas, it can, when it adsorbed on the surface, it can readily diffuse into the lattice. Once it diffuses into the lattice, it can actually become some kind of a defect inside the lattice. Now it is an interstitial hydrogen defect. Okay, now where will it go? It is more affinity towards the oxygen vacancies which are there, and it will kind of bind with present there and the interstitial sites. And correspondingly, now this is another donor or another uh, some other defect which has created as compared to previous one. Some kind of equilibrium will take place between oxygen hydrogen getting adsorbing, uh, penetrating inside the lattice, equilibrating all over, and you are getting some kind of a saturation in your current measurement. So all these things are basically changing dynamically, and after a long time this thing happens. So what we were seeing, you can see from this graph, beyond a concentration of 200 ppm, the response time was actually independent of concentration. So anything lesser than that, at 200 degrees, it was fairly changing, but after that it didn't matter how much gas concentration was there outside. So what understanding we developed was as follows. You have this ZNO microcrystal, okay, and you have oxygen which is surface adsorbed, which leads to surface state. That surface state has formed some kind of a depletion, and I have multiple such needles which are joined together, and the current takes its own path. Now when I put in more oxygen into this particular lattice, more oxygen gets adsorbed on the surface. So where will this oxygen bind? It will bind at the surface vacant sites, the deficiencies, the defects which are present on the surface. Those are the active sites where it can readily take up. Now once that takes up, your some of the charges are trapped into this tap state and your current decreases. So this decrease in the current, when you expose it with the hydrogen being an electron donor, it reacts with this surface adsorbed oxygen, the current increases. Once sufficient hydrogen saturation has happened on the surface, the hydrogen concentration gradient develops. There is a large concentration of hydrogen on the surface, and there is zero concentration of hydrogen inside the lattice. So that concentration gradient basically drives some kind of a diffusion of hydrogen inside the lattice, and this hydrogen diffusion basically reduces to some extent the surface adsorbed hydrogen, which leads to reduction in the current. Again a steady state is reached. Where will it reach? There is an equilibrium for a given concentration of hydrogen between incoming hydrogen and outgoing hydrogen. So this hydrogen will reach to some kind of a steady state, and then once you remove this hydrogen, the things will go back to its oxygen native state where only oxygen is present. All the hydrogen will somewhat dissolve from the surface, leading back to regeneration of the current. So this hydrogen incorporation is also a kind of defect, but that donor impurity may not be as um it may not have the same amount of donor strength like the oxygen vacancy, which can donate 2 electrons and have multiple. So the current may not actually come back to its own strength. So that's how we did this. The next thing is, this is one of the system which we have developed in our lab. It is on the same system, same zinc oxide micro rods. We have developed this Kelvin probe system, which measures the work function of a solid. Now, here the probe was brought from Germany. The rest of the vacuum system and all the arrangements for the sample heater, uh, optical excitation, gas change, gas environment, everything was done here. So what it has, it basically has some kind of a tip which oscillates onto the sample surface, and the tip is made in such a way that it makes some kind of a parallel plate geometry like a capacitor. And when the tip oscillates at a given frequency, it the capacitance formed because of these two parallel surfaces, that also oscillates. That sets in some kind of a back current into the system, and when you apply a opposing bias, you are basically nullifying that current, and is actually same as the difference between the Fermi level of the two things, that is the tip and your sample. So it is called as a contact potential difference. So likewise, we actually evaluate what should be the work function of the sample if you know what is the work function of your tip, which is a stainless steel tip. So for which the manufacturer has actually given the tip work function, which has been measured. And we calibrated the system with gold and other standard sample and so on. What we did was, for the same zinc oxide, we excited with super band gap excitation. Now the band gap of zinc oxide is somewhat 3.3 electron volt, and if you shine on with a light which has higher energy than 3.3 electron volt, uh, which is higher than the 3.3 electron volt, you are causing super band gap excitation. That means you are basically exciting one of the electrons from the bound state to the conduction band. So you have effectively generated a photo carriers, that is a hole and an electron pair. So this contributes into the current. However, this raises the carrier level in. So we have so this is routinely employed in photo response of ZNO. What we are basically we have done here is that we have tried to look at the work function response. People usually look at the current change, and then they quantify whether the sensor is good or bad. Now, but hardly anything is known about what changes the recovery of this signal, because once the photo carriers are generated and you remove the light, the photo carriers are going to get annihilated back. Now, or they are going to be taken by the electronics. So in the process, what happens this, when this electron hole pair is generated, you can see that the electron is already in the n-type crystal, where there are already excess of electrons. So it is very unlikely for the electron to recombine with the minority carriers, but it is very likely that the hole which is generated can combine with one of the, or annihilate with one of the majority charge carriers. So one can actually look into this. So where can so the signal which is actually not recorded by the electronics is basically the signal which is trapped in the surface states. So the oxygen which is present in the surface can actually take up some of these photo generated electrons, can also uh, basically trap these electrons and reduce your current. So the recovery can actually be influenced by your surface states. So what we have done is we have looked at the response and work function for different oxygen partial pressures. You can see one is in the ambient condition, one is in the full oxygen, and the other is in complete nitrogen. You can clearly see that the tail, that the recovery that they have varies like this. So this is the faint blue is actually 100% oxygen. This is somewhat 20% oxygen, the ambient, and this is nearly 0% oxygen. You can see that the current or the work function actually takes very long time for this recovery when it is having absolutely no oxygen in the atmosphere. So that means when there is oxygen in the atmosphere, once these photocarriers are generated, some of them are trapped by these oxygens. This helps into recovery of the photosensor. So that is why this atmosphere is basically tuning the response function of your photosensor device. Now the next thing what we did was, if there are these minority charge carriers, holes which are generated and they can readily recombine with the majority charge carriers, leading to losing some part of photocurrent, how much distance can they travel before they annihilate? That is called as the diffusion length of these minority charge carriers. So we have in this system we can actually excite the sample with multiple wavelengths. So we have 360 nanometer, 320 nanometers, and 530 nanometers. Also we are trying to get different wavelengths. So what we do is, we look at the response in the wave work function with different wavelengths, and parallelly from the UV visible spectrum we have already quantified the absorbance alpha value for given wavelength. So all both these processes, so the surface photovoltage, that is the change in the work function for given photon flux, that means normalized by intensity, normalized by area, all this is plotted as a function of alpha value for a given wavelength. Like for example, this is for the 530 nanometer, this is for 360, and this is 360 and this is 320. All these, when you have such a graph, you can draw a line and see where does it intersect the x-axis. The x-axis intercept gives you the diffusion length of these minority charge carriers. So effectively it is very useful for solar cells and photovoltaics and things like that, or photosensors, because once these photocarriers are generated, for solar cell you want to extract out that charge and you don't want to lose them in a recombination. So you want to optimize your thickness of the sample within the diffusion length of the minority charge carrier, such that it is extracted out by the electric field or the open circuit voltage that you are measuring. So then next topic where the defects we have actually seen is basically 2D materials, a single sheet of MOS2. I'm sorry, this is getting very dark here. I just have to switch on the light. So this is our recent work, which was done in collaboration with some of the people from IIT Kharagpur, IIT Kanpur, and IISc. And those metallurgists actually prepared high entropy alloys. These alloys are high entropy in the sense they are, as I mean, like there are mix of various elements, and their configurational entropy is really high because they can really they are disordered systems. So practically on a large scale, again, it is uniform. So these nanoparticles of around 4 nanometer, 5 nanometers were put in onto these MOS2 sheets. MOS2, if you look at the band structure, it would actually, whatever reports have said, it should have an N-type conductivity. That means it should have some sulfur vacancies. Sulfur vacancies will give some kind of donors and impurities, and the donor impurities will give you carrier concentration of electrons. Now, what we instead found is that from the response, it was showing p-type conductivity, which was contradictory to what we expected. And on the other hand, to differentiate between the part MOS2, which did have these high entropy particle and which did not have these particles, was showing very different electric behavior. You can see from the IV, one of the IV for the bare one without any particle was MOS2 was linear, and the other one was non-linear. So the linearity or the non-linearity basically quantifies the nature of the contact, whether it is ohmic or Schottky. The Schottky contact is something which is not bidirectional contact. It is characterized by an energy barrier between the metal and the semiconductor, and the electrons can come in from semiconductor to metal, but from metal to semiconductor side it encounters a barrier and it is not possible. So what we analyze these IV graphs from this thermionic emission model, which is routinely used for evaluating the barrier height. And what we found is that when the particles are put on MOS2, it actually shows a Schottky behavior with a barrier height of about 300 milli electron volt, and that barrier height is significantly high for room temperature as compared to the bare MOS2, which is around 100 milli electron volt or so. So how does that reflected into the response to hydrogen? This Schottky barrier and is very sensitive to hydrogen. You can see that the sample which had these particles, indeed, I mean, in effect, which had this Schottky barrier, actually was much more responsive to hydrogen. One of the reason is, first of all, catalytic effect of all these particles. They can be very good catalyst, and that can actually decouple these hydrogens effectively, which leads to spillover effect. On the other hand, one of the IIC researcher collaborator, he did a DFT on this to calculate how much should be the absorption energy of hydrogen on bare MOS2 and that of the MOS2 having these multi-component particles. And what we found was that the energy for these particles was much more lower than that of the bare MOS2. That means it can readily absorb this hydrogen, and that absorbed hydrogen can actually give a large change into the current. Because another reason was that you have a Schottky barrier, and even a smaller increase in the carrier concentration on one side can actually result into a larger current. So that kind of amplifies your change in the current, and what we saw is that something like 10 times enhancement in the response to hydrogen, and that was communicated to nanoscale. So the last topic where I am dealing with defects in the thermoelectric is basically thermoelectric transport. Just I will give a brief overview of thermoelectrics in general. Thermoelectrics means you have we all have studied Thomson effect, Seebeck effect, Peltier effect in our undergrad and in our high schools rather. So the Seebeck effect and Peltier effect together is called thermoelectric effect. Seebeck effect, when you have a temperature gradient in a sample, some of the carriers on the hot side, they'll excite to higher energy level because of the thermal energy that you have. You can see the hot side here. So there'll be excess carriers on one of the side compared to the colder side. This difference in the carrier density basically drives a diffusion current from higher concentration to the lower concentration. And when this carrier goes into the other side, let's say many electrons have traveled from hot to the colder side, this becomes negative and this becomes positive. This voltage, the electric field which sets up, basically again drives a opposite drift current. And given what is the electrical conductivity of the material, the electron will be able to go from one side to the other, or it will not be able to. So for example, in insulator, the resistance is quite high. You will see that the voltage, first of all, the temperature gradient that you apply, it sustains. So the diffusion also takes place, and the current does not really affect your generated thermo EMF. Okay, whereas in metals, the electrical conductivity is high, the thermal conductivity is also high. The thermal conductivity equilibrates the temperature very quickly, so that your temperature difference is smaller. On the other, again, your electrical conductivity is high, which ensures that a lot of it goes back, and your Seebeck, the amount of voltage that appears for a given voltage is reduced. So all these quantities together are quantified in thermoelectrics, and various materials people have been using. And the prime equation for thermoelectric efficiency is S square sigma by kappa by T into T. S is Seebeck effect, the Seebeck coefficient of the material. Sigma is the electrical conductivity, kappa is thermal conductivity, and T is temperature. So the thermal conductivity again has two parts. It can be the heat can be either carried by the phonons, or heat can be also carried by the carriers, the electrons or the holes. So this we call it as the electronic component of thermal conductivity and the lattice part of thermal conductivity. The lattice part of thermal conductivity is practically dependent on the sample and the defects and your crystal structure. You can see that the phonons which get excited for different defects have been shown here for as a function of frequency. The grain boundary, which is a 2 to 1 probability, Whereas if there are rattling ions in a bigger void, it has much higher lower frequency of vibration. It can actually scatter phonons of a particular frequency. There are nano-sized particles. If you kind of have grains, inclusions inside a foreign material inside the solid, it will scatter the phonon also, because you have altogether different crystal arrangement which is starting inside the new inclusion. And then you have a point defect scattering. You can imagine the point, you can see that point defect scattering is the largest at very high frequency, because these are associated with single lattice points. So their frequency bandwidth can be actually large. So it all these parameters are evaluated in our lab. We have studying various systems. This is one of the system which I am showing you right now. It is a complex double perovskite lattice. A perovskite, when I say, most of material scientists would readily say that it is AbO3 type structure. It is it is basically a cubic structure where there is A atom which is at regular corners and B atom which is at the regular faces, and O is at the regular faces and B is at the center. So however, in this case we have A dash B2 O6, something like that. So you can imagine there are two perovskite unit cells joined together, because that is where the repeating unit changes. So these are double perovskites where there are regular periodic arrangements of barium oxide, copper oxide, rare earth oxide, and like that. The beauty of this thing is that the oxygen from the rare earth oxide plane is very mobile. It depends highly on the oxygen partial pressure outside. And as a function of temperature, if you look at this system, it undergoes some kind of a lattice distortion at 340 Kelvin. And that lattice distortion brings in non-zero density of states near the Fermi level, which makes it conducting as opposed to the insulating state. So whatever was having very high resistance in the high temperature, suddenly it shows a drop in the resistance and it becomes more conducting. It shows a metal insulator transition. So this is what we have measured in our lab. This is in the metal insulator transition depicted in the resistivity. It is we have developed a system which can measure Seebeck coefficient of a sample of various kinds. So far, we have made it up to room temperature to 300 Kelvin. We are also extending it up to 1000 Kelvin. It can also measure it as a function of ambient gases. And we have done the measurements on different delta value samples, the different oxygen content of the lattice. And we have evaluated what should be the Seebeck for like that. And effectively, you can see that the Seebeck coefficient depends on the oxygen partial pressure, because oxygen partial pressure decides how much occupancy of oxygen will be there in the lattice, and correspondingly the valence of the cobalt in this particular system changes. That, I mean, parallelly it gives rise to different magnetic property. That apart, it gives different electrical properties, as in if you look at the whatever transition I just now mentioned will happen only for the region where there is delta value which is close to 0.5 plus minus 0.1 or 2. Rest of the things will show you a insulator like RT. So that means that there is a critical dependence of thermoelectric system onto oxygen partial pressure and the delta value. So we have studied this with spectroscopic X-ray photoelectron spectroscopy. And what we found is that we have proposed some oxygen sensors which are based on thermoelectric principle. This has been communicated. You can see that as you go on changing the oxygen partial pressure, you get much more robust than the electrical conductivity measurement, because electrical conductivity is hardly changing, because there is some kind of a boundaries. At grain boundaries you will have more easy access to the oxygen, so the oxygen can actually percolate from the grain boundary to a certain subsurface region, and up to that you will have a different delta value compared to the bulk. And essentially, if you are looking at the transport across these grains, you will see that the heavier holes the holes which are the holes which are having higher energy, not heavy, that is a different thing. The holes which are having higher energy can actually go through. However, the holes which are less energy will be trapped inside some kind of a potential well. So like for electrons, the potential well is down, for the holes it is upward. So which basically kind of discriminates between the holes which are low energy and high energy. It's called as energy filtering. So this energy filtering process basically leads to change in the seebeck quite efficiently as compared to your conductivity, because the surface is anyway conducting. The current can actually take bypass the bulk and can take the outer path. So if rather than measuring the electrical conductivity, if one opts to measure the just give a small temperature difference, what we had given was only 1 Kelvin, and for 1 Kelvin whatever voltage developed was measured in different oxygen ambiances, and particularly it showed these changes. Lastly, as ma'am mentioned, I like to make instruments, and I make it a point that the students kind of get. I mean, this I have inherited from my PhD guide. The first thing that our lab people used to do is make some instrument for themselves. So that actually helped me in setting up my own lab. We have developed quite a lot of systems for different measurements in the lab, and most of them are homemade, right from deposition system to measurements and characterization. I mean, of course, the X-ray, XRD, XPS, all that we do it out. I mean, in the CIF, which is a commercial machine. But all these measurements which I have been measuring, the gas sensing, the Kelvin probe, the sputtering systems, the chemical vapor deposition, seebeck, electrical resistivity, all such things, they have been made in my lab. So and it makes, first of all, it costs you less money, then it gives you better insight, and the students learn much more about the system and the process than using a black box where the sample is where the sample is put and the data comes out. And effectively it trains them to think uh, more insightfully about the systems. So I would basically summarize this talk with these key points. The defects are there in the real solid. They are inherent. They cannot be bypassed. Their concentrations, their distribution, their kinds might vary, but they will be there because we are at finite temperatures. So, and then they manifest themselves into different, the way, the property, whatever the physical property you are measuring, it will have its own manifestation. It can be seen into electronic, it can be seen into thermal, it can be seen optical, magnetic, it can be seen mechanical transport, mechanical bending or hardness and things like that. And they can be engineered. So there are various ways one can actually engineer: by surface treatment, by heat treatments, by chemical treatments, and various things. So one can engineer these things and exploit them for various applications. Lastly, I would like to thank many people here. First of all, to begin with, let's go back chronologically. My current lab members, the students who are the working horses, they are doing this work, and we are basically doing various things parallelly. My collaborators sitting in different universities and places around, and which help in kind of these things, and my institute for facilitating many things, including the student support to the lab space, to the everything, and the constant encouragement to kind of work. My alma mater, who have trained me particularly to uh, for whatever I am today. Uh, the IISc Bangalore life, which I kind of lived in the 5 years of PhD. My supervisor trained me in various things. My lab seniors, which were next to my, I mean, just one step down the supervisor, because they taught me various things, right from writing the paper to communicating it, and all such things, and of course doing the experiment, getting things done, and so on and so forth. My university department training for the 2 years, whatever I was there. Particularly, I would like to mention uh, the department atmosphere was conducive, as in it helped me do my MSc. Otherwise, it wouldn't have been possible. for my own various, some family reasons and all that, I had to work when I was doing my MSc, and it was not possible to attend classes during the, say, MSc part 2. And so I was doing some kind of a part-time job, and I took formally permission from the HOD then, and I spoke to various faculties, even my teachers, which used to come to teach us from colleges, particularly I would mention Vidya ma'am, and they told me that you can continue your uh, MSc while doing the job, and by provided you do the lab, you can, if you can work hard for the theory classes and make up by yourself, you can do it. And I used to leave from my office by 12 o'clock in the afternoon and reach Kalina campus by 1 o'clock. By the time the lectures were almost over, whatever I could get, I would just enter the class and sit, and then join the lab and get the things done. For the makeup for the theory. All this thing was possible because my teachers were very well. I mean, they understood my situation and they helped me. So I am really thankful to them. I am thankful to particularly Professor Kothari. Uh, he has been a guiding star. Mr. Ma'am, she has encouraged me all throughout. My interaction was more of with these people when Professor Radha also had just joined the department. She also uh, we used to exchange a lot of details, because when she was in the earlier affiliation of her, we used to go there for the classes and so on and so forth. Professor Rangwala has been kind of an inspiration. I used to look at that man and the energy and all that he would sport at when he was like at this age. I was amazed, and it was really inspiring. He used to teach us classical electrodynamics. He would come with a piece of paper where things were written, and practically he would just hardly look at them, and he would go on teaching. The honor of the talk today, Professor Press. I'm really, I remember, as I've been mentioning this from the beginning, I'm quite overwhelmed, and I have become nostalgic for those, this thing. I remember Iyer sir, Rita ma'am, Dubey sir, all these people who have been helpful during the labs, and they helped me actually achieve whatever I wanted at that time. That it was there in UDP. Somebody was writing form for ISC entrance, and I asked her, "What is ISC?" She said, "Okay, you don't want to know. You just fill up this form." I filled up that form and got admitted in ISC, and then on the life took a different turn. I'm thankful to all these people uh, for making contributing into this journey of mine. I just skipped one thing. I'm thankful to these funding agencies which are now funding my lab work, and they it is really, I mean, worth some, because without funding support, it's very difficult to do the experiment. So of course, I'm thankful to them. This is our campus. I'm sure most of you would love to be here. You're more than welcome. Just write to me sometime. If you can visit for a day, we can plan something when this pandemic and things are over. So basically, the faculties, I'm really making the invitation. And this is a picture. This is the time outside now, around 7ish, and that's how the campus looks like. Thank you. I would